So thank you very much for the invitation. I am very happy to be here, even though only on Zoom, and to talk to you about this recent work that I have done with Fedor Popov and with Jakob Sonnenschein, which was a new subject for us. So to try and look at the relation between integrable system and deterministic chaos, which it seems strange at first if one think about it, because integrable system and chaos seems to be two competing concepts. They don't seem to get along very well, and I'm going to show that in a sense this is not entirely true. And actually this is not true because it is not entirely clear how to correctly define what we mean by chaos. So all of these will be explained in a moment. This is a table of content, so I will start by actually talking about chaos and integrability. This will be the largest part of the talk, actually, and try to give some definition and motivation for why we want to look at these two concepts and why we want to understand how they are related one to the other, if they are related, and if they are in contrast, in which situations. Then I will give some simple examples, which relates to classical mechanics. And then I will begin showing systems in which chaos, or at least certain features of chaos, arise together with integrability or exact solvability. So I will give some simple examples of dynamical processes in which this is the case. And then I will move to integrable field theories, which are systems with an infinite number of degrees of freedom. And as I will show, the presence of this infinite number of degrees of freedom gives room for this chaotic feature to actually arise. And in particular, because this inverse scattering map, direct and inverse scattering map, are actually unstable, and they inject chaos in the system. So I'm sort of giving away the punchline here, but for whoever read the article, they know that was the main point. And then I will have some conclusions and some outlook. So this will be kind of an introductory talk. I hope it won't be too complicated. And if anyone has any question, please interrupt me and ask them. I will try to answer as best as I can. All right. So let us start by talking about integrability. Very on the surface, what we mean by integrable dynamical system is essentially a system that possesses a large enough amount of symmetry, or equivalently of dynamically conserved quantities, so much so that the solution of the system can be found by quadratures. So this is the core of Liouville theorem. Liouville theorem tells us that if we have dynamically conserved quantities, then we can use this conservation equation to perform a quadrature, so to integrate out a degree of freedom, so one of the degree of freedom will be the conserved quantity, which will be fixed, and associated to that, there will be a variable which changes with time, but changes with time in a very simple fashion, usually linearly. And one of the other aspects of integrable system is that the trajectories are regular. Usually they are periodic. There exists a concept of periodicity in the trajectories of the dynamical system, and the extension that Arnold performed of Liouville theorem states that in integrable system, the phase space is foliated into tori. So it is foliated into the spaces that have half the dimension of the original phase space. Sorry, two-dimensional tori in a number that is half the dimension of the phase space. So if our phase space, for example, is 4-dimensional, in an integrable system, we will have two tori. And these tori are characterized by the dynamically conserved quantities, which is one of the variable, and the other variable is an associated angle variable. And this is the action angle map that maps us from the original coordinates of our phase space to coordinates where the system evolves in a linear way. Now, one aspect of this foliation is that this structure is not stiff, even though the integrability is a rigid concept. So if we try to deform a theory away from, to deform a theory which is integrable, usually we break the integrability of the system. However, the structure of foliation that we observe in integrable system is not stiff, and this is a result by Kolmogorov, Arnold, and Moser. They show that the small perturbation of integrable system preserve the foliation almost anywhere. Now, however, it is also true that if we consider large perturbations of integrable system, usually the dynamics is radically different. And this has been observed in a number of examples, these two facts. Now, to give you an example of which is not the usual two-body problem, I thought of talking about, showing you the simple pendulum, which is very simple. Now, the simple pendulum, the simple mathematical pendulum has a phase space which is two-dimensional. We have the angle of oscillation of the pendulum and its momentum, which parameterize the phase space. And since we always have one conserved quantity, the system is automatically integrable. Any system which has a one-dimensional coordinate space is automatically integrable because the energy is conserved. A system in which the energy does not depend on time, of course. Now, if that's the case, then what we can do is that we know how to write the energy. We know that the energy doesn't vary in time. It's a constant. So we can perform a quadrature. And the quadrature takes the form that it's on the right. The integral can actually be performed exactly in terms of elliptic functions, and one can actually plot a solution. Now, what we see when we look at the solution, we see that there is a very irregular structure. There is an oscillation which has the same amplitude in time, and it just evolves in the same way forever. Now, contrast this with the double pendulum. Now, the double pendulum is much more complicated. First of all, it has a phase space which is four-dimensional. It has only one conserved quantity. So we cannot solve it exactly. We can perform a single quadrature, but this is not sufficient to, actually the p's here and here should have a square. I forgot about it, but it doesn't matter. And what we can see when we look at the trajectories, we see that they are very, very complicated. They don't seem to follow some predictable pattern. We can look at it in this form or in this one here. We see that there seems to be an oscillation, but the oscillation doesn't seem to have any kind of regularity. These systems seem to be chaotic, right? We would like to make this statement more precise, and I will come to that in a moment. But let us look, for example, at the phase space. Now, on the left-hand side is a phase space of the simple pendulum, which is very regular. It has this attractive structure with some ellipses in the center and some trajectories which continue forever. This should be looked at the left-hand side and the right-hand side should be glued together because this theta is actually an angle variable. On the other hand, on the right-hand side, we see the phase space trajectory, one phase space trajectory of the double pendulum. And we see that it really seems to be all over the place. There doesn't seem to be any kind of structure for it. So it has some element that we naturally intuitively associate with the concept of chaos. All right. So let us talk a bit more about chaos. What do we mean when we say deterministic chaos? Now, it turns out that actually defining correctly, or at least operatively, what we mean by chaos is very slippery. It's very complicated. It's very difficult to actually pin down mathematically the definition. So one of the perspective that we will use is sorry? Oh, okay. One of the perspective that we will use we use in this talk essentially boils down to this statement by Lawrence that the present determines the future, but the approximate present does not approximately determine the future. So in this phrase is contained the concept of determinism, which is the sense that the present determines the future. but also of chaos, because if we approximately know the present, then we cannot approximately determine the future. Now, this more concretely boils down to the idea that the chaotic systems are systems that are very sensitive to initial conditions. In the sense that if we consider a bunch of trajectories that start near each other, they will separate exponentially with time. So this is an old idea that goes back to the PhD thesis of Lyapunov, and mathematically can be stated as written here, so that the small interval at time t is exponentially related to the small interval at time 0. This, of course, is true up to the characteristic size of the system. So if the system is contained in a region of space, this cannot be true for an arbitrarily large time, but it will reach a saturation when it reaches the size of the system. But for sizes that are small compared to the size of the system, this is actually a very close approximation of what actually happened. Okay. Now, this is an example of what I mean by the diverging trajectories for the double pendulum. You see, I started with trajectories that were with points that were quite close, also in phase space here. And then you see that after some time, this point essentially span the size of the system. Now, here, the size of the system is constrained by the initial energy, of course. The system cannot, so the pendulum cannot go too far from this initial point, because there is a conservation of energy which constrains the size of this sort of bubble. But you see that the points actually span the size of this bubble. So this is what we mean when we say that the trajectory diverge. Now, it is clear from what I said until now that there is an apparent tension between the concept of integrability and the concept of chaos. So on one side, we have integrability is all about irregularity and all about predictability and periodicity. While on the other side, we have chaos, where we have the trajectories are irregular, they don't seem to follow any kind of predictable evolution, and there is an absence of recurrence. There seems to be an absence of recurrence. Now, the main reason, at least for us, why we are interested in trying to understand the relation between the two and the distinction between the two goes back actually more than 20 years. Less than 20 years, almost 20 years. Almost 30 years, sorry. To a result by Srednitsky. He showed in the case of finite dimensional system of many body systems that integrable systems do not thermalize on Gibbs ensemble. Or actually showed the converse. He showed that systems that have a chaotic behavior, as defined in the concept of as defined by Berry in 84, I think. Chaotic systems, the systems that are chaotic on a classical level, they at a quantum level thermalize on a Gibbs ensemble. And intuitively, integrable systems do not thermalize because of the behavior of the trajectory in the phase space. Now, it's clear if you think about it that thermalisation is very closely related to the concept of ergodicity. And ergodicity tells you that if you start somewhere on the phase space, if you wait long enough, the trajectories of this point you started with will span a constant energy surface on the phase space. Now, clearly, an integrable system will not behave in this way, because integrable system has phase spaces which are foliated in tori. So there are not only an initial point will not span a whole constant energy surface, because there are other constant quantities that constrain its evolution. On contrast, a system that does not possess any other constant quantity, in general, will have this property of exploring the whole phase space, or at least the whole constant energy surface in the phase space. So it's quite clear intuitively at least why this result is true. However, I want to stress the fact that careful definitions are very important, especially if you think about a situation in which we are given a dynamical system, and starting with, we do not know if the system is integrable or not. Now, how do we tell integrability and chaos apart? Now, clearly, as an integrable system does possess trajectories that can start very close but can diverge with time. And that's because even in integrable system, there exists patterns in the phase space which are called saddles, so points around which the trajectory move in different directions. So you can see an example here. So the question is, how do we tell apart integrable systems and chaos, supposing that we don't have any idea if our system is integrable or chaotic? Now, these are the definitions that we employed in our article. So we will use the concept of integrability, which is slightly broader than the usual definition, and it's more akin to the exact solvability definition. And I wish to remind here, and this is just a reminder, that the concept of exact solvability and of integrability are two distinct concepts. Usually there are certain differences, which I'm not going to get into. But for the sake of the talk, I'm going to say that the system is integrable if there exists a method that allows us to solve the theorem, in particular with a finite number of quadratures or with algebraic manipulation. So this concept of integrability, this definition comprises also the Liouville integrable system that I talked about before, but also includes certain example of dynamical maps that I will mention later. And on the other hand, I will say that this system exhibits deterministic chaos if for any initial state, one can find some small deformation that drives the system away under time evolution, at least in a weak sense. So, which means that the deviation of the trajectory that start very close grow and are unbounded. Note that this needs to be true for any initial state. There should always be a small deformation that we can make to the initial state of a system, no matter what initial state is, such that this deviation will grow with time in an unbounded way. And this is a definition that was used by Guggenheimer and Holmes in 2013. Now, paired with this definition of a system that exhibit deterministic chaos, there is a concept of a chaotic map which will be useful to us. We will say that a map acts on a metric space and map that to another metric space. M is the space and D is the distance. We say that this map is chaotic if I can find nearby point in the first space that are sent to distant point in the second space. So given any initial small interval and any large size L, I can always find 2 points in M1 that are mapped to distant points in M2. All right, so now that I'm done with definition, I will move to give some examples of chaos in integrable system. And I will actually start with a situation where you do not see chaos in integrable system, which are finite dimensional integrable system. Now, when we have a finite dimensional integrable system, as I said before, we have a set of conserved quantities. Here I'm thinking about Liouville integrable system specifically. And so we have these conserved quantities. These are actually, E denotes them. The phase space of the system is 2n dimensional. I have n of these quantities. This quantity Poisson commute. They also need to satisfy a concept of independence. They need to be independent, and they also need to be globally well defined. If these conditions are true, then we say that the system is Liouville integrable, and then we can perform quadratures and solve analytically our system. Now, as I mentioned before, there exists an action angle map. This is a map that takes your initial variable and maps them to other variables, half of which are these constant quantities and half of which are associated angles. And they are such that the variation, well, the time variation of the action variables is 0, and the time variation of the angle variable is linear. This is a canonical map, so it preserves the Poisson structure. We can do it, and then we can use this map, well, these mapped variables to solve our system, make it evolve in time, and then if we want, we can map back to the original coordinate. Now, if we suppose that the phase space we start with is a differentiable manifold, then this action angle map is finite dimensional and smooth by consequence. So this means that if we start with 2 points which are very close in the PQ variables, we cannot go to arbitrarily large distances when performing the action angle map. So what this means is that in finite dimension, any integrable system with a phase space which is a differentiable manifold cannot exhibit deterministic chaos, in the sense that we cannot have an evolution which maps small distances to large distances. Now here it's important to remark that I am imposing the fact that the integrable system is finite dimensional and that the phase space is a differentiable manifold. If we drop one of these assumptions, then it is easy to find example of integrable system that actually exhibit chaotic, some diverging trajectory.
Just to clarify, what does it mean that the map is finite dimensional?
The map?
Yeah.
Yeah, no, I'm...
Action angle map is
yes.
finite dimensional. What does it mean?
No, it's not the map, it's the phase space, but it's finite dimensional.
Okay. Phase space is finite.
Yeah, the phase space is finite dimensional. And if we also suppose that the phase space is differentiable, then this map that I perform, it's a canonical map. So it's a map of coordinate in my phase space. And this cannot blow up arbitrarily a small interval. So this contrasts with my definition of chaotic map and my definition of chaos, which means that in our convention, this cannot be chaotic. This cannot display chaotic features, or say it cannot have trajectory that diverge.
Yeah, sorry, Stefano. Presumably, presumably, Anton speaking here. Yeah, presumably, you assume that your symplectic morphism exists to the action angle variables, because to the assembly of Villar-Arnold, you would need to find it. It's not always possible, assuming that it exists at all.
Yeah,
right?
yeah. There is also that hidden assumption. Yes, I'm thinking about. Well, I mean, the examples that I have in mind in this case are simple systems that have
which are probably reducible to SOV and well defined in this sense.
Yeah, no, exactly. This is another point that we didn't take in account in our work, but it's something that we want to actually explore a bit further. It's the idea of separation of variable, which is not something necessarily doable in all integrable system, at least system that we say are integrable. And this becomes very problematic when you try to go into infinite dimension, even more problematic. Yeah, and I guess it has some bearing also on these things that I will say in this talk. So yes, I don't have much to say on that, but yes, it's something that we have in mind and we want to understand it better.
Sorry, do you have some extra assumptions like that the Hamiltonian is bounded from below or something like that?
Oh, let me think. Well, no, there is an assumption that not even the Hamiltonian can also not be in principle conserved. You just want to have an conserved quantities. Now I don't have any example in mind in which this is the case. But no, as far as I can tell, no.
Can a saddle be integrable?
I'm sorry, say it again.
Saddle, like Hamiltonian describing some kind of saddle dynamics. Yes, be integrable. like you have, let's say, two-dimensional harmonic oscillator
Yes.
with one frequency purely imaginary.
Yeah. I see. I would say yes, because you can consider it to be integrable in the sense that you can solve it exactly. So yes. Well, I mean, yes.
Sorry, Stefano, I think you're considering so far that's Hamiltonian integrability, that's classical. Mitya probably is asking for quantum, and this bound positivity is a different constraint, which is
he mentioned. That's what is meant. Okay, no. Yeah, then yes, I'm considering classical systems. Yes.
But still, this Hamiltonian is not positive, and effectively, phase space is not compact. In contrast to normal Hamiltonian with bounded.
Yeah, but I don't think.
And that's why.
Yeah, I don't think that changes the argument. Even
but
if
it would allow for maps which are what you call deterministic, chaotic, which take something small distance.
Yeah, so I see what you mean. You say that if we wait long enough in time, there is enough space in the phase space to actually have divergent trajectories, more or less.
Yes, exactly.
Yeah. Okay. Yeah, it's a valid argument. Yeah, I am not sure at the moment. I need to think about it, but yes, it might be. It's.
I think it's always possible in classical one.
I'm thinking about it, but the point. Yeah. Okay. No. Yeah, you're right. I didn't think about it. It's something I should think a moment on that.
Even if you have just a free particle, if you start with different momenta, and you evolve it in time, they spread, right?
Yeah, they spread. They spread. Yes. Okay. So probably that should be taken in account in some way in the definition if we want to include this. Yeah. You're right. Okay. Yeah. This is actually a good point. Thank you for that. All right. So for the moment, let us think of them as being compact manifold. But yeah, you're right. Okay. So returning to, if there are no other questions, if I can go on. So returning to what I said, if we drop the assumption, for example, the assumption of compactness, that it's not here, but it should be here, then we can find this divergent trajectory. If we drop the assumption of a differentiable manifold, then it's easy to see that there exist systems that have this chaotic behavior. So for example, the pinball problem is a famous example of this situation where we have a system that is integrable in the sense that at any moment in time we know how to let the system evolve further in time, and because it's everything is just free motion with some elastic scattering at the boundaries of these disks. So the system is integrable according to the definition that we gave, but the system is also chaotic, and that situation arises because the phase space is not smooth, because we have these regions that are inaccessible to our particles, which are given by the disks. Okay, so we saw that if we drop one of these assumptions, we actually can find chaotic behavior. And also if we drop the other assumption, which is that the phase space is finite dimensional, if we drop the assumption that the phase space is finite dimensional, we will see that we can also have chaotic features arising. And as a warm-up, let me give you an example of a discrete time dynamical process. This was actually the initiating example that we had, and that started the whole idea of studying this relation between integrable system and deterministic chaos. And the example is the Baker's map. So the Baker's map is a very simple map. It takes a square to itself in the way that is depicted here. And the evolution of this map is chaotic, is quite renowned as a map, and this can be seen in this animation here. You see, if we start with 2 points that are very close, if we wait for a long enough time, then we see that the 2 points spread to the size of the system, and there is a mixing among all the other points, as you can see here. So the system clearly is chaotic according to our definition. However, the system is also integrable. And it's integrable in the sense that there exists a map that takes us from the position variables to these auxiliary binary variables. These sigma i's are binary variables, and I have a string, and a doubly infinite string of them that parameterizes my the binary representation of x and y. And now, if I study the Dressed map, the Dress-Baker map, I see that this acts as a right shift. So in this case, any totally symmetric function of the sigma i's is conserved. And I also have a procedure to solve algebraically my system, because I perform first the map to binary representation, then I let the system evolve, and it evolves in a very simple way, and then I map back to the position variable, and I have the time evolution. Now, one thing that I want to stress here is that the system seems to be both integrable and chaotic, and the chaos arises because of this map to binary representation. Because the dynamics in the binary space is clearly not chaotic. Small sequences that differ by a small number of ones and zeros, they keep on differing by this small number of ones and zeros. However, if we map them to the position variable, then these two sequences will map to very different points, and vice versa. So this is an example. If I take two numbers that are very close to each other, 1 over pi and 81 over 256, then these have a binary representation which is hugely different, because after a certain point, here is after the eighth sigma 8, to the right, the 81 over 256 has only zeros, while 1 over pi has an infinite number of ones, distributed in a non-repetitive way. And clearly, when I let these two sequences evolve in time, the two numbers at some point, 81 over 256, will just go to 0. The map will, this map is characterized by the fact that any fraction that has two powers of 2 in the denominator eventually end up at 0. While 1 over pi will keep on roaming the whole square for an infinite amount of time. So here it seems that it's this map. It's the map that maps us from a space in which the dynamics appears to be complicated to a space where the dynamics is very simple. That is the map that injects chaos in the system. And we will see that this is what happens also in integrable field theories. Now, as an example, let us take the KdV equation. The KdV is one of the prototypical integrable field theories, and this is an equation that is solvable with a procedure which is called inverse scattering transform, usually. And the procedure is is actually on a level of principle. It's very simple, because the only thing that one should notice is that the auxiliary scattering problem, which is written here, which is just a Schrödinger equation which is with a certain potential and with some boundary conditions for psi, is related to the KdV equation if we allow the various quantities of the scattering data to evolve in time according to this. So in other words, we can recast the KdV equation into the compatibility condition of a differential operator in x, which is this Schrödinger operator, and a differential operator in time, which tells us that U should evolve according to KdV, and the data of this scattering problem evolves according to the right-hand side of the slide. Here, I only wrote the scattering problem for the unbounded state, but there might be also bound state in the system, and they can be formally obtained by changing k to I kappa. And now R becomes B, and T in this case is infinite. Now, once we have this time evolution of the scattering data, we can choose an initial profile at time equals 0. We find the scattering data at time equals 0. We let it evolve in time in a very simple way. And then the problem is to reconstruct the potential. Now, fortunately, there exists a procedure, which is due to Gelfand-Levitan and independently by Marchenko, which is an integral equation that allows us, given the scattering data of a Schrödinger problem, to reconstruct the corresponding potential. So, in other words, this inverse scattering transform essentially is a nonlinear Fourier transform. It takes our system at some initial condition, and instead of making it evolve in the field space, which is very complicated because the dynamics is nonlinear, it performs a direct scattering transform to some auxiliary data, which in this case is the scattering data, let it evolve in time in a very simple way, and then performs an inverse transform, which maps us back to the field space. Now, the point is that these maps, just as it was the case for the map to binary space before, these maps are chaotic in a sense. And this is actually something that was already known since the 80s in the field of geophysics, which is quite surprising. At least it was surprising when we found out. In this context, the inverse scattering transform, the same inverse scattering transform that is used in this system, is used to reconstruct the potential given the waves that are measured by instruments, and so essentially infer from the patterns of wave that are measured, infer which is the structure of the medium that is conveying this wave. And what they remarked is that this inverse scattering transform is extremely sensitive to errors in the data that is collected, which is another way to say that the map is unstable or it has some chaotic feature. Now, the fact that direct scattering is chaotic, it's another thing which is quite easy to understand. And this is due to a very well-known fact. It's actually something that is mentioned in Landau and Lifshitz in the third book of the series, that given a scattering problem, if we add any small well or bump in our potential, then these will map to additional bound states in the scattering problem. So this means that if we modify we can modify our initial profile very slightly and have a drastic modification of the initial data, which will then evolve in a way which is drastically different from the other configuration that we started with. Now, this is due to the fact that the scattering in one and also in two dimension is strongly coupled in the sense that it's presented here. So let's suppose that we have a very small potential. So we are considering a situation in which we have a potential that is deforming the zero potential. Then in this case, we can expand psi in this way, just as a plane wave plus some small variation, which satisfies this linear equation here. And now this linear equation is solved in this way. And we see that there can be arbitrarily large correction which come from the infrared spectrum. So when k is very close to zero, then this delta psi is not small. It can be arbitrarily large. So in this sense, the direct scattering problem is chaotic. It doesn't allow for small deformation of the potential can lead to very large deformation of psi, and consequently of the scattering data, and consequently of the time evolution of this data and of the time evolution of the field. So to give you an example, sorry, I will just jump. I had some backup slide in the case I was in time. I will make a very simple example by considering the modified KdV equation, which is another integrable equation, which is actually connected to the KdV equation through a change of variable. And I want to show you, just to show you the plots of a solution which is periodic in T, which is called the Breather solution, and has this initial profile, phi1 at t equals 0, and then a small modification of this solution, which is the same one, minus some function that affects this small deformation of the initial profile. So it adds this very small indentation at x equals 0. Now, on the right-hand side, you can see a plot of the difference between the two functions as they evolve in time, and you see that the evolution in time seems the difference seems to grow. So, well, I mean, at least it bumps up. It doesn't stay very close to 0, as we might expect naively. So we can quantify this by plotting, for example, the L2 norm, so the integral of the absolute difference square. And what we see is that this difference, this is a quantity that quantifies the distance between the two solutions. And we see that this quantity actually grows in time. Now, if this growth is exponential or not, this is not something that I did. This is a very quick computation that I did in Mathematica yesterday, so I don't have an answer for that. But we can clearly see that there is a growth in the difference between the two solutions. And this is related to this idea of that I mentioned before, that small bumps in the initial profile bring about bound state in the scattering problem, which then translate into diverging evolution of the solutions. Okay, so to go back, the last thing that I want to mention is we can actually gain a more concrete feeling of the instability of the direct and inverse scattering map by computing the conserved charges. So this relates to the idea that I mentioned when talking about the Baker map, that if we start with very close number in the Baker map and we do the binary transform, we end up with very different sequences of with very different binary sequences. And here the idea is the same, is that we can define the conserved charges, which are somehow some equivalent of these binary sequences in some way, and they are defined through some recursive relation which involves the field U and all its derivatives. And then we can go and try to compute the difference with the charges in two situations where U is 0, which is very simple because all the charges are 0, and then a very small Gaussian, which we can make arbitrarily small. So this Gaussian is distance from U is of the order of 10 to the minus 1. And we can see that the first charges are actually small, but the more the index of the charge grows, the more the size of the charge grows. So this is the same situation as we see before. We have a dynamics which is non-chaotic in the scattering space because it's a linear dynamics, but the inverse and direct scattering map are what inject chaos in our system. All right, so coming to conclusion, what we showed in our work is that integrable system can show behavior that are typically associated with chaos. And this happens because the map from initial condition to the conserved charges in general is responsible for this instability, for these chaotic features, for the arisal of this chaotic feature. And actually this happens whenever we have a situation where there is, as I mentioned before, enough space for the trajectories to actually diverge. In the case of infinite dimensional phase space, there is enough space in the neighborhood of a trajectory to actually have two trajectories that are close to each other but actually belong to manifolds, submanifolds that diverge at later time. This is very hand-wavy and intuitive, but it's somehow how I think about this situation. Now, of course, there are a number of directions that we would like to look at in the future, and one of these, of course, is to look at the chaos in the quantum system, so try to understand, if possible, the relation between integrability and chaos at the quantum level. And another thing that we might want to do is to explore more refined measures of chaos. Now, this whole work, it's in some ways very simple-minded. We started from a simple and somewhat naive definition of what we mean by chaos, which is just that I have trajectories that diverge in time. Now, evidently, this definition of chaos does not give us the distinction between what we mean by integrable and what we mean by chaotic. And in particular, from the point of view of wanting to understand the concept of thermalisation better, wanting to have a way to predict if a system will or will not thermalize on a Gibbs ensemble, then this measure of chaos that we use is not sufficient. It doesn't work as we want. So we need more refined measures of chaos. And this relates back to the fact that chaos is a very complicated concept, and it's very difficult to pin down. And to actually, well, there are hierarchies of chaos. There are systems that have are defined to be softly chaotic, systems that are defined to be hardly chaotic, and it's difficult to disentangle exactly them and say, well, find observables that actually tells us which system has certain behavior and which has other behavior. Well, an example of a more refined measure of chaos can be, for example, studying the statistics of trajectories. Now, here I study the trajectory per se, but one way is to study the statistics of them and to try to infer what is the behavior of these statistics that gives us a chaotic or a non-chaotic model. And then, of course, well, there are some systems that have non-differentiable phase space that have appeared in the literature in the high energy theory recently, so like the zigzag model, which was introduced by Dubovsky and Jack Donahue recently, and the TT bar model, or the TT bar deformation, which I worked on for a long time and has been of interest in the high energy community for a long time, well, since 2016 actually. And the TT bar and all its cousin deformation, these irrelevant deformations, they all have classically a phase space which is non-differentiable, that has singularities, that has this kind of non-smooth structures. So it might be interesting to try and look at them from this the point of view of what I mentioned in this talk. And then, of course, refining what we did here is one of the steps that we want to take. So I don't remember who mentioned here, of course, the idea that the phase space need to be compact in order to have integrability and not chaos. This is something that we didn't think about, but it's something we should probably point out, and so on. So, well, thank you very much for your attention.
Thank you. Are there any questions?
Yes. Open this. Okay.
I have a question, or as far as I understand, the chaos is introduced by this map from original variables to, say, action angle variables or something.
Yes.
So it may be depending on what kind of observables you're looking at, or which correlators of these observables, etc. So it may be that if you just look at observables which depend only on this action angle variable, they will not exhibit any chaos, right?
Yeah. But this is very much let's say one of the core questions here is one of the argument that one can have against, for example, what I mentioned in, say, the Baker map. No, where is it here? Is that, well, I mean, but the system itself is not chaotic because it evolves according to this law, which is not chaotic at all, right? So, and this makes perfect sense. It's a good statement, and it's fine. But the point is that we choose what we want to look at in the system. So we need to, like you said, we need to have if you want a preferable set of observable that are of interest in our system, because I don't know, maybe our system describes the position of a particle in some kind of experiment, so we want to look at its position. And then if that is our goal, then if we look at them, we see chaos in our system. And that's the same thing that you said. If you choose to look only at the observable that in an integrable field theory depend on the conserved charges, then it's clear that if we have, say, all zeros conserved charge and we just modify the 13 conserved charge by a very small amount, dynamic of the system will not change much, right? But on the other hand, if we try to go and look at the position that our system has in field space. So if our observable are in that space, then the differences are very big. So it is very much a matter of perspective, which is probably what makes the process of disentangling integrable system from chaotic systems difficult. And it is even more difficult when you are in infinite dimensions, where you actually have the freedom to do these things.
Yes. So, for example, in 2 dimensions, you can imagine you have 2 different due representations for the same integrable system, like, I don't know, sine wheel, or some todas, or even tearing sine Gordon.
Yeah.
And you may not. Yeah, they may share some integrable structure in some way, but they may be different as far as this chaos definition.
Yeah, no, I agree. And yeah, one thing that I didn't mention at this thing at the quantum level, there is a similar perspective in the sense that when you go in a factorized scattering perspective, what you do in an integrable system is that you define a basis of particles, right? And then you go and study how these particles factorize. So in the case of sine Gordon, you have solitons and breather and multi-solitons that form the basis of your particles. But then if you choose an initial state which corresponds to, say, a Gaussian profile, an initial Gaussian profile, then this will correspond to a superposition, usually an infinite superposition of solitons, which means that its scattering will be somewhat chaotic because it involves a huge number of particles, even though the scattering between 2 particles is factorized and it's perfect elastic and whatever you want. You still have a system that effectively behaves as if it was chaotic. Which is somehow a reflection of these, probably of these classical concepts that I mentioned here. So yeah, it's quite complicated, I have to say. We had to think a while about these concepts.
Excuse me, can you say that all of this, I'm also asking about the last question of Arkady. Can you say that this is all of this is related to locality? Say, for example, Arkady suggested you can add something to your action angle variables, and you can define your observables as functions of action angle variables, but these observables will be non-local. Can you say that if you consider local observables, they will be kind of chaotic?
What do you mean by non-local?
So
you mean like integrated variable, integrated field variables or something like that?
No. I mean that Arkady suggested to construct observables from action angle variables, from scattering data. In other words.
Yeah. No, I agree.
But RK I defined non-locally.
So well, but in some sense, no, because this Q. So it depends on what you mean by local, but these Q are the integral of a local. So these are local in some sense. Or you mean non-local in the sense that you're performing the integral and then you need information on the whole space variable?
No, actually I mean that I mean that your argument was about the scattering data, and you usually find them locally by solving the Schrödinger equation in the entire potential.
Okay. Yes. No. I understand.
I don't know about these charges, so probably you can say that this transformation is local in space. But in KdV equation, you usually perform an essentially non-local transformation.
Yeah.
So
yeah. No, I understand. I understand your point. Yes. So the core, yes, as I said before, is the fact that these maps are chaotic because these maps are very highly nonlinear and very highly non-local in the sense that you meant. So yes, if you think, I don't know if you know the representation of a solution U in the case of sine Gordon, for example, there exists a formula of sinh Gordon, actually, a formula that takes the solution of a sinh Gordon equation is the sum over an infinite number of terms each term is n convoluted integral of some function and some kernel and whatever. This is an extremely complicated, extremely nonlinear and non-local transformation, which gives you the field from the conserved charges.
So is it that the question, basically my question is it locality that is related to chaotic-like behavior? The fact that we
it
consider...
Yeah, I am sure that there is a connection between the two, but again, the point is that you, in some sense, these charges that you define here, you can take them as being local. You can define, or you can take the fields as being the local observable that you want to look at, and then it changes the, well, let's say that the kind of results that you obtain, or at least in the sense that I said before. So you can have a dynamic which is linear, but still, when you look at the observable that you want to look at, because you do this non-local transformation, in a sense, then you find that the dynamics is actually more similar to a chaotic dynamics, or it has some feature of chaos. Yes. So yeah, I expect there to be a connection between the two, but at the moment I don't know how to specify it.
Thanks.
Yeah, sorry, Stefano. I think there are a few points in relation to previous questions. I'm just wondering, because I think what Arkady said, it really depends what kind of chaos and how does it develop. Namely, like you say, would you expect, for example, suppose we have this prescription for constructing conserved charges in the T2-bar deformed models.
Yes.
Well, would you expect there would be any similar behavior to this? But I would say it would be different of nature. I mean, if I want to connect this, maybe to separate a little, to connect this to some, I don't know, say SYK or some other irrelevant, if you want this that dynamical data. But here, because it's one thing, but here, if I would be looking all this chaoticity that is arising at the level of the conserved charges for this system, like is arising through the behavior, if you want, through the recursion of the fields.
Yes.
Which is reflected, of course, in the conserved charges. I'm just wondering, because this probably could lead just to two different type of chaos.
Oh yeah. Oh yeah. Okay. There is one thing
in the nature. I mean, like.
Yeah. No. Yeah. Nature. Yes. Okay. The nature of chaos is there is multiplicity there. Like there are different kind of chaos, and like one thing that we would like also to understand is the relation between these kind of chaotic features that we see here, the chaotic features that arise when you deform your model, right? You can deform your model, say free field or whatever you want, in various ways that break your integrability, and then you have additional type of chaotic features. You have this transition to chaos that is described by KAM theory, KAM theory, and so on. But you also have,
but
you also have where you have this connection to SYK, and yeah, that's another thing. That's it's
because there you see it's like still yet they are integrable, because we have the flow equations. Everything is conserved. Like this is irrelevant. Yes, we have opposite flow, but this type is just, I would say, at the level of SYK we can even connect this to geometry if you want.
No, that I agree. So
where here in classical it's more algebraic in a sense, and how it is evolving in time.
But I agree, it's a different flavor of chaos, and trying to understand if it's related. I don't think it is directly, but it's another way of trying to understand what chaos is. And
no, sure, but I see your point. Good. Maybe other generic point is, do you think, I don't know if you have thought about, could it be implemented, I don't know, or checked for the instanton sector? I don't know, like, I don't know.
Yeah, we didn't think about it.
Self-duals.
Yeah, we didn't look at that. As I said, it is a very somehow simple-minded contained experiment that we did. But yes, there are other things that we want to look at.
Because this is just one class, and you will immediately get all the topological solitons and everything you mentioned.
Yeah. That's a good idea, actually. Thank you.
Okay, anyway, sure, thanks.
Can you say, as a summary, that, well, essentially the notion of chaos is ill-defined, right? So because it essentially depends on the, let's say, it's coordinate dependent, depending on what dynamical variables you pick, you either have it or you don't have it.
Yeah, in some sense it is. And no, I would say that it is more like, it's more akin to the idea that what we want to define as chaos is related, is very strongly dependent on the description that we employ of our system, right? So I have a very, very vague idea on that. It's just coming out of the things that we saw, and I still haven't pinned it down completely, but it is very much, as you say, dependent on the coordinate, in the sense that we choose certain adapted ways to describe our system because of reasons, because we want it to be solvable, or we want it to have certain features, or to exhibit certain symmetries explicitly, or something like that. And that has a bearing on what we define as chaos, at least in this talk, in this work. It seems to have a consequence on that, which is strange, because at first you should think that this seems to be, it should be an intrinsic characteristic of your system, but evidently it doesn't seem to be the case, right? And for me at least, it's very difficult to try and disentangle this. I would like to understand. That's one of the reasons why we went in this direction, because we would like to actually have a definition which does not depend on how you look at the system. I have no idea if that is something which is doable at this level, if it requires a different kind of definitions or something like that. That at the moment I don't know. But it reminds me somehow this old thing that Alexander Zamolodchikov told me once, that, well, if you take a system, whatever is dynamical system, you can always map it to a free system. You just have to have an incredibly complicated map of variable, but in principle you can. And then
any system or any integrable.
I mean, that's what I never tried to do that. Any system. That's what he said. This was related to the idea of TT bar, that you can use. I don't know if anyone here knows, but these kind of deformations at a classical level, at least, you can either look at them as very complicated deformation of the dynamics of the action, or you can look at them as a geometric deformation, where now your space-time, the coordinate that you use to describe it, depend on the energy of the system itself. So you have some sort of self-interacting geometry there. But in that coordinate, the system is free. Or at least it's not deformed. So if you start with some model. And yeah, this is kind of similar concept.
So in finite dimensional case, there is the statement that any Hamiltonian using canonical transformations can be brought to the canonical form in which H is just P1, momentum along one.
Yes.
And of course, in that coordinate system, evolution is very simple. But this can be done only in the finite neighborhood of a point.
Yeah, no, I know it's not a global thing. No, I think it is. His statement was kind of an hyperbole, so it was not actually like to be true. But it's related to this whole question of there exists only one Hilbert space in infinite dimension, and you know, all these things, and then it depends on what you put on that. That's what defines your dynamics. That's what defines your observable and everything else. So yeah, as I told, this is very vague, and I cannot make it more precise at the moment. But just to answer your question, yes, there is a dependence on the way that you look at the system. So
Okay, thank you. Are there any more questions? Okay, if no, then thank you for a nice talk.
yeah, thanks to you. It was very kind of you to invite me, and yeah.